Hello everyone, I'm Dr. Engineering. Welcome back to the VHDL tutorial series. Today, we'll be covering two fundamental digital circuits, the half subtractor and the full subtractor. These are the basic building blocks for performing binary subtraction, which is critical in digital systems like computers, calculators, and more. By the end of this lesson, you'll understand how these subtractors work and how to design them. A half subtractor is a simple digital circuit that subtracts two single-bit binary numbers, producing two outputs, the difference and the borrow. The A input is the minuend, the number from which we subtract, and the B input is the subtrahend, the number being subtracted. The circuit outputs a difference, D, and a borrow, bout, if the minuend is smaller than the subtrahend. This is the truth table for a half subtractor. When both A and B are 0, there's no difference and no borrow. If B is larger than A, like 0 to 1, we have a difference of 1, and we need a borrow. If A is greater than or equal to B, the difference is either 1 or 0, but no borrow is needed. Now let's look at the logic expressions for the half subtractor. The difference output, D, is generated using the XOR gate, where a XOR gives the difference between the two inputs. The borrow output, bout, is calculated as not A and B, which means if B is 1 and A is 0, a borrow is needed. What is a full subtractor? A full subtractor is a more advanced circuit that subtracts two binary numbers, A and B, but also accounts for an additional borrow input, bin. This is necessary when the subtraction involves multiple bits, and a previous subtraction has already borrowed from a higher bit. Just like the half subtractor, the full subtractor has two outputs, the difference, D, and the new borrow, bout. Here's the truth table for a full subtractor. As you can see, the full subtractor takes into account the borrow input, bin, when calculating the difference and the new borrow. For example, when A equals 0, B equals 0, and bin equals 1, the output difference will be 1, and a borrow will be needed. The difference output for the full subtractor is generated using three inputs, a XOR B XOR bin. This gives us the correct difference even when a borrow is involved. The borrow output is a bit more complex, combining three different conditions. If A is smaller than B, or if there was already a borrow, another borrow is needed. To summarize, both the half subtractor and full subtractor are essential building blocks in digital circuits. The half subtractor handles basic 1-bit subtraction, while the full subtractor is designed to manage multiple bits and borrow inputs. These subtractors are commonly used in larger systems like arithmetic logic units, ALUs, and processors. Now that we've mastered the basic concepts, let's open Vivado to design and simulate the actual circuit. Today, I'll demonstrate the process using a full subtractor as an example. As before, we start by creating a new project for the full subtractor, and the steps are the same as when we created any other new project. In the source panel, we'll create a new VHDL design file. Based on the block diagram of the full subtractor that we just introduced, we'll define the input and output interface names. Since they are all 1-bit signals, we'll define them as 1 bit. Here, the VHDL file is created. Let's open it. Let's align these ports first. To make it easier to check and analyze later, we'll define three intermediate signals, which will be of type wire. According to the equations, we will first assign these intermediate signals used in the equation for borrow out, B out, to these intermediate signals. After that, we'll define the relationship for the output signal, difference. With that, the circuit design file is complete. Now, let's go back to the source panel and create a new test bench to test the functionality of the circuit. Following the same steps, we create a VHDL file named full_subtractor_TB. Let's open the testbench file. Similar to what we did in the full adder chapter, we'll define the corresponding test signals for the inputs and outputs. For the input signals, we'll use the prefix R to represent them, equivalent to register type signals in Verilog. These signals will connect to the inputs of the circuit. Likewise, for the output signals, we'll use the prefix W, similar to wire type signals in Verilog, and these will connect to the outputs of the circuit. Next, we'll define a constant for the clock period, which will help us set up different combinations of input signals during the test. In the begin section, we'll instantiate the unit under test, UT, of full subtractor, and we'll map the test signals to the input and output interfaces of the UT. Just like with the full adder design, we'll define 3 independent input signal processes, with each one running at a period that doubles with each step. These processes will execute independently, continuously looping through themselves. Now that the test bench is complete, we can save everything. And set the simulation time to 100 nanoseconds. Click Run Simulation in the navigator, and after a moment, we'll see the simulation waveform. By clicking Zoom Fit, we can adjust the waveform display to fit the window. Finally, we compare the simulated waveform with the truth table. If all the conditions match, it means our design is correct. And with that, our full subtractor design is complete. Now it's your turn. Open up Vivado and try designing your own half subtractor or full subtractor. The best way to learn is through hands-on practice. Don't forget to experiment with different input signals and explore the simulation results. Good luck! That's all for today. Practice makes perfect, so keep experimenting and soon you'll become FPGA experts. If you like this tutorial, please subscribe my channel for more useful information. See you in the next video.